Good day, ladies and gentlemen. You are welcome to our first lecture on Cmen308, which is measurement and instrumentation. As we all know, the measurement techniques, they have been in existence from the beginning of the human civilization, because whatever you are going to sell, whatever you are going to buy, whatever you are going to maybe harvest in the farm and what have you, it has to be measured. Therefore, measurement started having importance from our beginning of life on Earth. Then, during the 19th century, there was what they call industrial revolution in the Europe and the Western world in general, and that made the measurement very, very important, because whatever we are going to use in the factory to produce, to manufacture, it has to be measured in some way. And the measurement, as we all know, if you just mention a figure, maybe let's say I have 10, I have 20, it cannot make any sense. I have to say 10 kilometers, that is a distance. 10 kilogram, that is mass. So we have our quantities and their SI units, as we all know. Like the mass is in kilogram, like the distance is in meter, like the time is in second, and what have you. So the measurement has three areas of application. The first one, it is used in regulating trade. As I said, whenever you are going to buy something or sell something, it has to be measured. Maybe the volume, maybe the weight, maybe the length, and what have you. Even the labor, maybe you can pay the laborers per hour or per day or something like that. And also it is used for monitoring functions. For instance, we have control systems, monitoring systems in hospitals where the blood pressure, the temperature of the body are all being measured by doctors in order to know the condition of a patient. And the third one is it is used in feedback control system. We know control is divided into open loop and closed loop. The closed loop is the one in which we have a feedback from the output. So these are the three areas of application of measurement. So the next thing is the block diagram that shows the element which are used in any measurement system is given here. As you can see here, this is our sensor. That's the actual device that will detect the parameter we want to measure. Then we have another equipment for variable combustion. Maybe it will take it in a mass, something, change it to electrical signal. Then we have signal processing. The signal produced also, it has to be further processed by either amplifying it or attenuating it to meet up with certain standard. And then we have our output of the measurement here. But in some cases, this output is not taken at this point. It has to also pass through a transmission medium and finally go through another processing, and then presentation of the signal is done. It can be displayed and it can be stored in a recording medium. And how do we choose appropriate measurement instrument? There are so many factors we use in choosing any measurement instrument. We have measurement accuracy, we have resolution, we have sensitivity, we have dynamic performance, and we have environmental conditions like temperature, pressure, and what have you. And we have ruggedness, that is the durability, and of course the ease of maintenance and the low cost is or are some of the reasons why we select any measurement instrument. Let us start looking at, we're going to look at these ones one after the other later. Now, the instruments are divided into different classes according to several criteria. The first class is we divided the instrument into active and the passive instrument. The passive instrument, they are the ones that the actual indication of the reading we see is produced by the actual quantity we are measuring. But in the active measuring instrument, what we see at the output is not exactly what is detected by the sensor from the parameter we want to measure, but rather the parameter we are measuring, it is used for changing something in the circuit, then a corresponding output is produced. Example of the passive measurement instrument is the pressure measuring device shown here. If you look at this one, I have a container in which I have a fluid, and this is my piston which is blocking the fluid, and here I have a spring. whenever the pressure of this fluid increases, definitely it is going to push this piston upwards, and when it does that, it will make this pointer move along the scale. And we can see that the actual pressure of the fluid is the one that is causing the movement of the pointer. So we call this one a passive measurement instrument. Then on the other hand, the active one is example of a plotting type petrol tank level indicator. If you look at this, we assume this is our petrol tank, and this is a plotting device. That's something that will not sink in the petrol because it is light. Now, whenever the level of this petrol is going down, definitely this pointer will be moving, and when it is also going up, the pointer will be moving, but its movement is just along one leg of what? Variable resistor. So whenever it moves downward, it is increasing the resistance. If it moves upward, it is decreasing the resistance. So in this way, the only thing that this level of petrol is doing is to change the resistance of this resistor, and based on this, corresponding voltage will be produced according to what is the value of the resistance at that point. So we can say that the reading we are seeing from this instrument is not produced directly by the level of the petrol, but rather by the movement of the pointer along the variable resistor. So this is what we call an active measurement device. Then we also divide them based on the indication type. We have null-type and we have a deflection-type. The deflection-type is the one in which whenever the variable we are measuring changes, there will be a movement of a pointer along the scale, just like the pressure measurement device we have just looked at. Whenever this fluid level pressure increases, definitely it will compress this spring, and this one will be moving so that we can see the reading. So this one is a deflection type because there is movement of a pointer along a scale. Now the other one, the null type, is the one in which we want to balance the something at 0 point. We have a scale, we call it pan scale, for measuring weight. If you go to buy maybe a nail or building or anything, they will put a standard weight in one of the pans, and they will put what you want to buy in the other pan whenever they balance. So it means they balance at the 0 position, and that is what we call the null type measurement instrument. And this is a typical example. We call this one deadweight pressure gauge. And as we can see here, the fluid, whenever the pressure increases, it will be pushing this thing upward, and on top of the handle we place some weight to balance it so that it will be at 0 point. So whenever it balances, we can now say the weight of this load is equal to the amount of force the gas is able to produce. Now, another classification of measurement instrument is with respect to analog and digital. Whenever we say something is analog, as we all know, it means the value is given in continuous form. Maybe if it can measure maybe between 0 to 5 amp, you can have a point where you have 1.1 amp, maybe 1.11 amp, meaning the readings are continuous, they are not discrete. Typical example is this pressure gauge we have been looking at previously. Now the other one, that is the digital instrument, the output, they are in digital form, they are in discrete forms, that is numbers, whole numbers. For instance, if you have, this is a cam, and the cam, as you can see, it is what? It has a big point here while the other points are level. So whenever this thing is rotating, whenever this cam comes, it will push this handle up, and by doing that, it will close this gap. Whenever that happens, we'll have a reading of 1 here. When it goes around again and come to this point, you have 2, which means whatever happens in between, they are not being recorded. It's only the whole numbers 1, 2, 3 like that. So this is a digital instrument because the output are in discrete form, while the other one, they are in continuous form. Now we have what we also call another classification. We have what we call the indicating instrument, and we have a signal output instrument. So the difference is that the indicating instrument, they are the ones that will give you output that you can see visually, or they can give a sound to show that the measurement is taken. But the signal output instrument, they are the ones that actually they don't require your presence. You don't need to hear or feel. They are used in such a way that when the measurement is taken, they are now delivered to a system that we use them for a particular purpose. So we can now say the indicating instrument, they require somebody to be around, because it is how it is human being that we hear the sound, or it is human being that can see the indication. But in the signal output type of instrument, the reading taken is not going to be displayed on anything, or it will not produce any sound, but rather it will be used as a part of another system that will be controlling something. So in this case, whenever the reading changes, the signal, it will be delivered to that system it is being controlled. It will be changing the operation, either the speed or anything of the system under control. So these instruments are commonly used as part of the automatic control system, that is the feedback control system, as I've just said. Now we have another classification of measurement instrument, the smart and the non-smart. The smart instrument or intelligent instrument, they have microprocessor and extra sensors. And the reason why they are called smart is that they can detect any error, systematic error introduced by the environmental factors or anything, and they can now produce a counter signal that will cancel the effect of that error. But the other ones, the non-smart, they are the ones that they don't have that facility. Now we come back to static characteristics of a measurement instrument. The static, whenever you say something is static, it means its value doesn't have to change with time. It is independent of what? Changing time. And these parameters include accuracy, sensitivity, and linearity, and reaction to ambient temperature. So all these are called static because they are independent of what time. And whenever you're going to buy any instrument, measurement instrument, in the data sheet, all these characteristics are supposed to be spelled out. And we should know that the values that are given in those data sheets, they only become accurate whenever you use the instrument under the standard condition it is calibrated. If it is calibrated at 20 degrees Celsius, whenever you use it outside that temperature, maybe 40, 30, or 10, you expect those parameters to be inaccurate. Now let us start looking at the accuracy and its counterpart, that is inaccuracy. And the accuracy of any measurement instrument is the measure that shows how close the output you are taken from the instrument is to the correct value. For instance, if you want to measure the voltage of a battery which is labeled 9 volts, so the closer to 9 volts the instrument is given, the more accurate it is. For instance, if it gives you 8.999, you see it is just 0.001 difference. So we can say this instrument have high accuracy. And in most of the measurement instrument, they give you the full scale reading of the percentage. That is, if it can measure from 0 to 5 amps, they will tell you that it has an accuracy of 5% over the complete range. And sometimes we are given the inaccuracy in the data sheet instead of given the accuracy. They will tell you that the accuracy of an instrument is within plus or minus 1%, which means the only error that we expect should not be within outside 1, not more than 1, not less than 1% of the full scale. Now, the other characteristic is the precision. We sometimes call it repeatability, and sometimes we call it reproducibility. The precision of an instrument, it shows the degree of freedom from random errors, how stable it is in avoiding random errors. The higher that value, the more the precision of the instrument. For instance, if you use an instrument to take several measurements at the same time, and those measurements are very, very close to one another, we can now say this your instrument has a high precision. But we should know that the precision is entirely different from accuracy. For instance, If you want to measure 5 volts, you know it is 5 volts. So when you instrument first measurement, it give you 3, second measurement it give you 3.1, third measurement it give you 2.9, like that. You see they are very close to another. We can now say the precision is very good, but we want to see 5 where it's seeing 3 or thereabout. So it has low accuracy but high precision. So precision is the ability to reproduce the value we are measuring. And the next thing is the tolerance. The tolerance of any measurement instrument is the amount of maximum error it can be expected to withstand before it causing any trouble. And of course, the tolerance is not a static characteristics of the measurement instrument. But the reason why we measure this is sometimes the manufacturers, instead of giving you the accuracy, they can give you the tolerance of the measurement instrument. So that is why we bring it here. But the tolerance is dynamic characteristic. And as I have said, the tolerance is the maximum deviation of the manufactured component from the specified value. That is to tell you that whatever you can measure from this, the error cannot be more than 1% or 0.5%. So it is giving you the accuracy, and of course, this is what we call the tolerance at the same time. Now, the next thing is the range or the span of any measuring instrument. The range of measurement instrument is the difference between the minimum value it can measure and the maximum value it can measure. And the next thing is linearity. The linearity of a system is a picture that shows how proportional is the input to the output. If the input and the output are proportional to one another, whenever you keep on taking different readings and you plot it on the graph, you have a straight line passing through all the points. So the closer all these points are to the straight line, the more linear the system is. And whenever you have 1 or 2 or 3 points very far away from the line, so in this case you can also start talking of what the level of non-linearity of the system. So the maximum deviation from that straight line is what we call non-linearity. And of course, I want you to know this. If we say a system is linear in engineering, what we mean, it possesses 2 fundamental characteristics. The first one is proportionality, and the other one is what we call the additivity. For a system to be proportional, it has to be in such a way that whenever the input increases by some percentage, the output is also going to increase by similar or very close percentage. That is what we call the proportionality. While the additivity, supposing you have an instrument whose input is x1 and it gives output of y1. When the input is changed to x2 and it gives the output of y2. So when your input now is x1 plus x2 and your output is y1 plus y2, now we can say it has what we call the additivity. And these 2 parameters are the fundamentals, the most important in detecting whether the system is linear or non-linear. So the next parameter is the sensitivity of the measurement instrument, and the sensitivity of the instrument is a measure of a change that the instrument output will experience as a result of input it has detected from the sensor. So the sensitivity is given as a ratio of the scale deflection, that's the movement of the pointer, to the value you are measuring from the sensor. Now, for us to understand this sensitivity, let us look at our example. The following resistance values of a platinum resistance thermometer were measured at the range of temperature. Determine the measurement sensitivity of the instrument in ohms per second. Now, this is the table. These are the resistances, and this is what the temperature. You can see that when the resistance is 307, the temperature is what? 200. 314, 230. 321, 260, and like that. You can see the difference between this and this is 7, between this and this is 7, and between this and this is 7. And also the temperature between this and this is 10, 10 all through, sorry, 30, 30 all through. So the sensitivity of this instrument should be equal to change in the resistance, which is 7 all over change in the angle 30 degrees. So we have 0.233 ohm per degree Celsius. This is the sensitivity. Now, the next thing is the threshold. The threshold of any measurement instrument is the minimum value it can detect and gives a corresponding output. Whenever you put any value below the threshold, that measurement instrument cannot detect it and it cannot show any deflection or reading. This minimum value of the threshold of an instrument, as I said, is the minimum that can give. For instance, if you have an ammeter and whenever the temperature is below 1 microamp, it cannot respond, then you can say 1 microamp is the minimum threshold of this instrument. And of course, sometimes the threshold values are given as a percentage of the full scale, just like the accuracy we have seen before. Now, the next thing is resolution. The resolution of an instrument is how clear the reading of that instrument is displayed. And just like our phone cameras of our phone, we have 3 megapixel, 10 megapixel, and what have you. The higher the number of pixels, the clearer the reading. So the resolution sometimes is given as a percentage of the full scale deflection also, and sometimes it is given just as an absolute value on its own. One factor that is influencing the resolution is how finely, how clearly the output scale is divided into subdivisions, just like our pixels. The pixels are those boxes on which the image is printed. The smaller the boxes, the clearer is the image to be produced. The next thing is sensitivity to disturbance. The instrument sometimes responds to environmental disturbance. Whenever you place it in any condition where the temperature is different from the one it is calibrated, or the pressure or humidity or anything, so you find that the output will change not only from the input you are taking from the measurement, the system you are measuring, but also from those temperature and pressure and other environmental conditions. Now, these variations, it occurs, as I told you, as a result of changing temperature or pressure or anything. And this sensitivity to disturbance is also a parameter that shows the magnitude of the change that can be experienced as a result of changing temperature and other environmental conditions. And as I said, these environmental conditions, they can now affect your instrument in 2 ways. We have what we call zero drift, and we have what we call sensitivity drift. And let us look at these two. And the zero drift, sometimes we just call it a bias. And the zero drift is nothing but is the effect that you will see on your scale when you didn't even connect the something you want to measure its magnitude. That is, you see a deflection if it is a continuous handle, where you have a value of maybe 0.0 this or 1 before you even connect your instrument. So this is what we call the bias. Sometimes we call it zero drifts. And what we do is we just adjust our instrument to make sure it is on the zero line before we take any reading. And this zero drift, it causes constant error to exist in your system unless if you balance it back to zero before taking any measurement. And when this your instrument is very sensitive to several environmental factors, maybe temperature, pressure, humidity, and what have you, then the zero drift that we have, it will have several coefficients. There will be a coefficient for temperature, for pressure, for humidity, and all the other parameters to which it is sensitive. Now, the sensitivity drift, which is the second one, we have zero drift, we have sensitivity drift, and sometimes we call it scale factor drift. It is the amount by which the instrument sensitivity will vary, will change due to ambient conditions change. And this sensitivity drift, it has coefficient that shows how much drift can happen in unit of the indication of the measurement instrument, depending on whether it is temperature or pressure or any other parameter that can cause that variation. If we want to understand the difference between the zero drift and the sensitivity drift, here is a worked example. A spring balance is calibrated in an environment at a temperature of 20 degrees Celsius and has the following deflection per load characteristic. This is the table. When the load is 0, the deflection is 0. When the load is 1, 20. When the load is 2, 40, like that. And it is now taken to another environment where the temperature is not 20, but it is 30. And that place we have seen that when the deflection, the load is 0, we already have a deflection of 5. When it is 1, we got 27. When it is 2, we got 49. And 3, we got 71. Now the question says we should find the zero drift sensitivity, and we get the sensitivity drift. Now, as we can see from this diagram, when the temperature is 20 degrees, the first table, the load characteristic is a straight line, because you can see when it is 1, 20, 2, 40, it is a straight line. So the sensitivity should be equal to 20 millimeter per kilogram, because the lower line here of the second row is in millimeter deflection and the other one in kilogram. So we'll say 20 over 1, or 40 over 2, or 60 over 3, and all of them will give us 20 degrees Celsius. Now, when the temperature has changed to 30 degrees Celsius, our sensitivity now changed to 22 millimeter per kilogram. And how do we get this? You can see that the difference between this and this is 1, but this and this is 27 minus 5, which will give us 22. And also here, 49 minus 27 will give us 22. 71 minus 49 will give you 22. So therefore, it is 22 millimeter per kilogram. Now, the zero bias drift is 5 millimeter, the one that we have here. Even before we attach any load, we have 5 millimeter. That is the no load deflection. Then the sensitivity drift, the one that is created when the temperature changes to 30 degrees Celsius, is the difference between this and this. That is 22 minus 20, which will give us 2 millimeter per kilogram. So now the absolute value of the zero drift is given by 5 over 10. And how do we get that? If you want to get that, look at our variation here between this. If you say this minus this, will give you what? Or rather, just look at the first one. It is okay. Here we have 5 at 0 load, so that is the deflection. And what is the change in temperature between this and this? The upper one is 20 and the second one is 30. That's the change in temperature is 10. So 5 over 10 will give us 0.5 millimeter per degree Celsius. While if you come to the sensitivity of the second one, you can see that the difference between this and this is 2. And also the change in temperature between the first one and second one is 30 minus 20, which is 10. So we get 0.2 millimeter per kilogram per degree Celsius. Now, the next thing is we have what we call the dead space. And the dead space of any measurement instrument is the range at which the input is changing but the output is remaining at 0. For instance, anywhere here you can see I have a value, anywhere here I have a value, but between this and this the output remains 0, even though the voltage, the input, is changing or increasing and decreasing at the same time. So the next thing and the last thing is the dynamic characteristic of measurement instrument. And as I have said, these are the characteristics that changes with the change in time, unlike the static ones. So the dynamic characteristics, they also have so many different ways they can affect your instrument. That is why whenever you're buying any instrument, apart from the static characteristics, which are time independent, also the dynamic characteristics are created. Those characteristics, those properties that can change whenever the temperature changes. So ladies and gentlemen, this is the end of our today's lecture. Thank you very much, and we are going to, God willing, meet in our second lecture. I advise you to read and read again and make sure you understand it. If you don't, go back again and read. That's the advantage of this kind of videos. Thank you very much.